What's going on, guys? Justin here, and welcome to our 16th example video following our course on differential equations. Now, I know this one's been a long time coming. We're quite behind on differential equations example videos, but I'm going to try to catch them up as I can, sprinkled in throughout the next coming weeks. And some of you might have noticed that I'm actually using a face cam for this video. Going forward, I'm going to try to make all the example videos have face cams because I hope it'll make the video more engaging for you to be able to follow along seeing me in person, as opposed to just kind of having that black screen from the iPad's recording. So let's go ahead and look at our theorem for this video. So this example video is going to be on series solutions for first and second order differential equations. Specifically, we are going to be using this theorem for all of the examples in this video. So the theorem is as follows. The coefficients, which are represented by the set a sub n in any solution which is given by y equals the sum as n goes from 0 to infinity of a sub n times x minus x naught to the nth power of the differential equation y plus alpha times the quantity x minus x naught squared times y double prime plus beta times x minus x naught times y prime plus gamma times y is equal to 0 will satisfy the recurrence relation where we have a sub n plus 2 is equal to negative p sub n over n plus 2 times n minus 2 times a sub n for all n greater than or equal to 0, where our p sub n is represented by the following equation, where p sub n is equal to alpha times n times the quantity n minus 1 plus beta times n plus gamma. Moreover, the coefficients of the even and odd powers x minus x naught can be computed separately in the following manner. We have a sub 2m plus 2 will represent the even coefficients, and that will equal negative p of 2m over 2m plus 2 times 2m plus 1 times a sub 2m, where m is greater than 0, and the odds will be represented by a sub 2m plus 3 is equal to negative p of 2m plus 1 over 2m plus 3 times 2m plus 2 times a sub 2m plus 1, where m is greater than 0. And we have that a sub 0 and a sub 1 are arbitrary. Great. So let me go ahead and get into the proof of this theorem, and then I will go ahead and apply it in 3 examples. So now that we've stated the theorem for this video, let's go ahead and get into the proof. So let's begin the setup for the proof for that theorem. So we will go ahead and start the setup for our proof by letting a capital L y equal 0. And additionally, we are going to let that capital L y equal the following differential equation. We will have 1 plus alpha times the quantity x minus x naught, and that will be squared times y double prime plus our beta times x minus x naught times y prime, and then finally plus a gamma times y. Great. And so from here, we want to observe the following. So we want to observe that if we have y is equal to the sum as n goes from 0 to infinity of a sub n times x minus x naught to the n, we have the following definitions for our y prime and our y double prime. So for our y single prime, we will have that is equal to the sum as n goes from 1 to infinity, and taking the derivative term by term, we will get n times a sub n times x minus x naught times n minus 1. And we will also get the following for y double prime. We'll have y double prime is equal to the sum as n goes from 2 to infinity of n minus 1 times n times a sub n times x minus x naught to the n minus second power. Great. So now we can use these series representations in our original differential equation, and we will get the following. So hence, we have the following series representation for our differential equation. We will have that L times y is equal to the sum as n goes from 2 to infinity of n times n minus 1 times a sub n times x minus x naught to the n minus second power. And that will be plus the sum as n goes from 1 to infinity of alpha times n minus 1 plus beta times n plus gamma, all times a sub n times x minus x naught to the nth power. Great. So from here, I want to note the following 2 things. First, we will notice that this is our polynomial p sub n from our original theorem, and we're going to call it such. And also we are going to need to re-index this first sum so that we can combine these two sums together. And so once we do those two things, we re-index our first sum and we represent that polynomial that I pointed out here as p sub n, we will get the following. So that will give us the following final value for our L times y. Here we'll have L times y is equal to the sum as n goes from 0 to infinity of the following. We will have from our re-indexing an n plus 2 times n plus 1 times a sub n plus 2. And then from our other term, we will have a plus p sub n times a sub n. And that will all be times our powers of x minus x sub naught, which was to the nth power. Great. So thus we can conclude that we have the following relationship. So thus we have that L times y is equal to 0 if and only if the following is true. We have that n plus 2 times n plus 1 times a sub n plus 2 plus p of n times a sub n is equal to 0. And this will be for n greater than or equal to 0. But we can rearrange that so that we have the following, which should look familiar to you from our theorem, that a sub n plus 2 is equal to negative p sub n over n plus 2 times n plus 1 times our a sub n, and that will once again be for n greater than or equal to 0. And thus we have completed the proof of this theorem. Great. So let's go ahead and get into our first example, applying this theorem to differential equations of this type. Great, so let's go ahead and take a look at this first one. So this first one says find the power series in x for the general solution, and we have the differential equation as follows. We have 1 plus x squared times y double prime plus 2x times y prime minus 2y is equal to 0. Great. So the first thing we want to do when approaching differential equations of this type is, well, note that they are differential equations of this type, but after that we want to extract our alpha, beta, and gamma from this equation. It's worth noting that for this differential equation, we do not have to worry about our x sub naught, and we are looking for power series in x, so we are good here. So the coefficient for our first term there, which will be our alpha, is just 1. So that means that we have alpha is equal to 1. Next, we want to look for our beta, and once again, that'll just be the coefficient of our second term, which will be 2. So we have that beta is equal to 2. And lastly, we want our gamma, which is just that negative 2 there. So we have our gamma is equal to negative 2. Great. So from here, we want to go ahead and plug these values into our p of n. So I'm going to go ahead and write out the definition of our p of n for those of you who probably do not have it memorized just yet. And so our p of n is represented in the following way. We have alpha times n minus 1 plus beta times n, and that will be plus gamma. Great. So let's go ahead and plug these values into our p of n and then see if we can factor some things out. So when we do that, that'll give us our following p of n for this differential equation. We have p of n is equal to just n times n minus 1, as our alpha is a 1. Then we'll have plus beta times n, but beta is 2, so that'll be plus 2n. And then lastly, plus gamma, but our gamma is a minus 2, so that will be minus 2. So let's go ahead and multiply this out and see if we can't factor some things out. So let's go ahead and multiply that n into the n minus 1 there, so that will give us n squared. Then we'll have a minus n, but we have a 2n next to it, so that'll just be a plus n. And then lastly, we will have a minus 2. And so our p sub n will factor as follows. We will have n plus 2 times n minus 1. So we're going to go ahead and plug that into our a sub n plus 2 formula from our theorem. So a sub n plus 2 is equal to, we have a negative out front, and then in the numerator we will have our p of n. So that will be n plus 2 times n minus 1, and that'll be over n plus 1 times n plus 2. So our n plus 2's will cancel out, and then that'll be times a sub n, and this will be for n greater than or equal to 0. Great. And so now we want to split up this a sub n plus 2 into even and odd coefficients. So let me go ahead and write out the definitions for the evens and odds. So in general, our evens will be a sub 2m plus 2, and that will be equal to negative out front. It'll be p of 2m. and that will be over 2m plus 1 times 2m plus 2, and that will of course be times a sub 2m for m greater than or equal to 0. And our odds will be given by the following. We will have a sub 2m plus 3 is equal to, keeping that negative out front, our numerator will be p of 2m plus 1, and our denominator will be 2m plus 2 times 2m plus 3, and that will be times a sub 2m plus 1 for m greater than or equal to 0. Great. So let's start by computing our even coefficients. So our even coefficients will be given by that first formula there. So let me just scroll up and keep that at the top. So that will be p of 2m. So I have that negative out front. So a sub 2m plus 2 is equal to negative. Our p of 2m will just be replacing our n's with m's, and if you recall, our p of n was n plus 2 times n minus 1, so that means our p of 2m will be 2m plus 2 times 2m minus 1, and that'll all be over 2m plus 1 times 2m plus 2. So our 2m's plus 2's will cancel, and then that will of course be times a sub 2m, and I'll just verbally say m is greater than or equal to 0. Great. So now we want to go ahead and calculate these coefficients to find our a sub 2m. So let's start with our first even coefficient, which will be a sub 2, keeping in mind that a sub 0 and a sub 1 are free. So when we have a sub 2, we will have m is equal to 0, as we have 2m plus 2. So when m is equal to 0, we will have the following in our numerator. Well, we have a 2m minus 1 in the numerator, so the m will go away, and we'll be left with a negative 1, but since we have that negative out front, it will cancel our negative 1, so we just have a 1 in the numerator. And our denominator is 2m plus 1, and the m will go away in that as well. So we'll simply be left with 1 over 1 times a sub 0. Great. And we don't want to simplify here because we are trying to identify a pattern. So keeping that in mind, let's go ahead and calculate our a sub 4 here, our next even coefficient. So when we have a sub 4, our m will be equal to 1. So let's go ahead and plug that into our equation. Well, when m is equal to 1, our numerator will be 2 times 1 minus 1, which is just 1. So we'll have a negative 1 in our numerator there. So negative 1. And our denominator will be, well, let's see, we have 2m plus 1. Well, if m is equal to 1, that'll be just 3. So we'll have negative 1/3 for our a sub 4, and that will be times a sub 2. So let's go ahead and substitute our a sub 2 into that as well. So that'll give us negative 1 over 3 times 1 over 1 times a sub 0. Great. So moving forward with our recursion, let's go ahead and calculate our a sub 6 until we have an idea of the general form of these coefficients. So when 2m plus 2 is equal to 6, that means our m must be equal to 2. So let's go ahead and plug that into this equation. Well, when m is equal to 2, 2m minus 1 will equal 3. So we will have a negative 3 in our numerator here. In our denominator, when m is equal to 2, we will have 2m plus 1. That is 5. So this will be negative 3 over 5 times a sub 4. But we already have a value for our a sub 4. So that will give us negative 3 over 5 times negative 1 over 3 times 1 over 1 times a sub 0. And I think you get the idea for the general form of our coefficients now. So in general, our a sub 2m will equal the following. We will have negative 1 to the m, because we have an alternating negative, as each term will pick up a negative. And that will be over 2m minus 1, as the numerator of each successive term will cancel out the denominator of the last one, and we will just be left with 2m minus 1 from the most recent. For example, in this a sub 6, we are only left with a 5 in our denominator there. Great. So now that we've calculated our a sub 2m, let's go ahead and do our odd coefficients next. So for our odd coefficients, we will be using that second formula, which I have still at the top of the screen, and that is p of 2m plus 1 over 2m plus 2 times 2m plus 3. Let's go ahead and calculate our p of 2m plus 1 first. So we have a sub 2m plus 3 is equal to, keeping that negative out front. So we're going to plug in a 2m plus 1 into our p of n. And if you recall, that is n plus 2 times n minus 1. So when we plug in a 2m plus 1 into our n plus 2, we will be left with a 2m plus 3. And then when we plug it into our n minus 1, we will just simply be left with a 2m, as our minus 1 and plus 1s will cancel. And then we will keep our numerator, which is 2m plus 2 times 2m plus 3. And our 2m's plus 3's will cancel. And this will be times a sub 2m plus 1. And once again, I will verbally say that this is for all m greater than or equal to 0. Great. So what we're left with for our a sub 2m plus 3 is negative 2m over 2m plus 2 times a sub 2m plus 1. So just like we did before, we're going to go ahead and calculate our coefficients to see what the general form of a sub 2m plus 1 is. Now, because a sub 1 is free, our first odd is going to be a sub 3. Great. So when we have a sub 3, m is equal to 0, so we're simply left with a 0 in the numerator, but because of the recursive definition of all of our coefficients, that will mean we will have a 0 times every single coefficient. But let's go ahead and show that just to make things simple. So we'll have a negative times 2 times 0 over our denominator, which is just going to be equal to 2 times a sub 1. And for our a sub 5, which will be our next odd, we will have the following. Well, when we have a sub 5, that means m is equal to 1, as 2 times 1 plus 3 is equal to 5. So that will give us in our numerator a negative 2, as the negative in front of the fraction will carry over, and the m is just 1 times 2. And then in our denominator, we will have 2 times 1 plus 2, which is equal to 4. So that will give us negative 1/2 times a sub 3. But you can see when we plug in our value for our a sub 3, it will cancel out all of the successive coefficients for our odds. So this means that a sub 2m plus 1 is simply equal to 0. Great. So now we can put these even and odd terms together to come up with our solution to this differential equation. So since our a sub 2m plus 1 is equal to 0 for all m greater than or equal to 0, combining these two coefficients will give us the following final solution for our differential equation, where we have y is equal to a sub 0 times the sum as n goes from 0 to infinity of the following. We will have negative 1 to the m plus 1 times the fraction x to the 2m over 2m minus 1, and that will represent all of the even coefficients. And then since our odd coefficients, a sub 2m plus 1 are equal to 0 for all m greater than or equal to 0, the only term we will have left is our arbitrary term, which will be a sub 1 times x. And that will be the power series solution to this differential equation. So let's go ahead and get into our second example. So for number 2, we want to find the power series in x for the general solution of the following differential equation. We have 1 minus x squared times y double prime minus 8x times y minus 12y is equal to 0. So just like the last problem, we want to extract the coefficients from this differential equation. So right away we can notice that our alpha will be equal to negative 1, our beta will be equal to negative 8, and lastly our gamma will be equal to negative 12. Great. So now we can plug these into our definition of our P of n. So our P of n will equal, we will have, let's see, our alpha times n minus 1, so that'll just be negative n times n minus 1. Then we'll have minus our beta times an n, or minus 8 times n. And then we will have our gamma, which is just minus 12. So let's go ahead and multiply this out and see how it factors. So this is going to equal, well, we'll get a negative n squared, and then our minus n and our minus 1 will cancel, so we'll have a plus n, which will give us a minus 7n for our second term here, and then we'll just be left with a minus 12. Well, this is going to factor in the following way. We will have this is equal to negative n plus 4 times n plus 3. And I think that this negative is actually going to help us out, because for all of our formulas that we have for our P of n, there is a negative out front, so that means we will likely be dealing with all positive numbers for the rest of this problem. Great. So let's go ahead and plug this P of n into our definition for our a sub n plus 2. Well, our a sub n plus 2 is equal to negative out front, but like I said, that will end up canceling. So we'll just write our P of n in the numerator. We will have n plus 4 times n plus 3. And that will be over our denominator, which is simply n plus 1 times n plus 2. And this will be times our a sub n for all n greater than or equal to 0. Great. And now we can split this up into even and odd coefficients, just like we did in the last problem. So once again, just like we did in the last problem, we will start with our even coefficients. So our even coefficients are going to be the following. We will have that a sub 2m plus 2 is equal to a negative, and then in our numerator, we will have p of 2m. So that will give us a 2m plus 4 times 2m plus 3 in our numerator. And our denominator will be the same. We will have 2m plus 1 times 2m plus 2. And that will be times a sub 2m for m greater than or equal to 0. And so from here, I want to note that we can extract a multiple of 2 from this first term here and this term here, which will give us the following definition for our a sub 2m plus 2. We will have a sub 2m plus 2 is equal to, well, I forgot to mention that these negatives will cancel. So that will give us a m plus 2 times a 2m plus 3 in our numerator. And our denominator will be as follows. We will have 2m plus 1 times, with that 2 taken out, just an m plus 1. Great. And that will still be times a sub 2m for m greater than or equal to 0. And so just like the last time, we want to go ahead and calculate some coefficients to figure out what the general form of this is. So starting out, we will have our a sub 2. So when we have a sub 2, our m will be equal to 0. So let's go ahead and plug that into our definition here. So when our m is 0, we will be left with a 2 times 3 in the numerator. And that will be over a 1 times 1 in our denominator. And that will be times a naught. Like I said, I'm not going to multiply these out because we do not want to simplify this. We are looking for the general form. So next, let's go ahead and calculate our a sub 4 here. When we have a sub 4, our m will be equal to 1. So our numerator will be the following. We will have a 1 plus 2, which will be 3. And that will be times 2 plus 3, which is 5. And then in our denominator, we will have 2 times 1, which is 2, plus 1 is 3. So that will be a 3. And that will be times 1 plus 1, which is a 2. And then this whole thing will be times a 2. Well, what does a 2 equal? Well, it equals 2 times 3 over 1 times 1 times our a naught. Great. So I want you to go ahead and notice that our 2 and 3 in the numerator of our a sub 2 will cancel out the 2 and 3 in the denominator of our a sub 4, and we'll simply be left with 3 and 5. So let's keep note of that as we move to the next coefficient. So just to make sure this pattern will remain, let's go ahead and write out our a sub 6 before writing down the general formula for our evens here. So a sub 6 will be equal to the following. Well, when we have a sub 6, m must be equal to 2. So when m is equal to 2, our numerator will be 4 times 2 times 2, which is 4, plus 3, which is 7. And that will be over 2m plus 1, which will be 5, times m plus 1, which will be equal to 3. Great. And that will be times our a sub 4, which, as we wrote above, will be 3 times 5 over 3 times 2, which is times 2 times 3 over 1 times a sub naught. And indeed, we have kept this pattern. Well, the numerators of each successive term will be canceled by the denominator of the next one. So we can write out the general formula for our even numbers now. So we will have that a sub 2m is equal to just the numerator of our fraction from the newest term, or which is represented by m plus 2 times 2m plus 3, and that will be times our a sub 0, which is carried from each term. Great. So now that we have our evens, let's go ahead and calculate our odds. So our formula for our odds is a sub 2m plus 3 is equal to, we will have a negative out front just like before, and then we want to calculate our p of 2m plus 1. Well, if you recall, our p of n is equal to n plus 4 times n plus 3 with a negative out front. So let's go ahead and start by canceling this negative here. So when we plug in a 2m plus 1 into n plus 4, we will be left with a 2m plus 5. And when we plug in our 2m plus 1 into our n plus 3, we will be left with a 2m plus 4. So that will finish off our numerator there. And our denominator is always the same. It is 2m plus 2 times 2m plus 3. And that will be all times a sub 2m plus 1 for m greater than or equal to 0. Great. So just like the last time, I'm going to factor out a 2 from this term and a 2 from this term to simplify our calculations for our coefficients. So this will equal the following. We will still have a 2m plus 5 as our first term, but once we factor out that 2 and cancel it with the 2 in the denominator, we will be left with an m plus 2 for our second term of our numerator, and that will be over an m plus 1 times 2m plus 3 times a sub 2m plus 1 for m greater than or equal to 0. So now let's go ahead and compute our odd coefficients. So let's start with a sub 3. So when we have a sub 3, our m is equal to 0, which will give us the following in our numerator. We will have a 5 times a 2 in the numerator, and in the denominator we will have a 1 times a 3, and that'll be times a sub 0. Great. And for our a sub 5, we will have the following. When we have a sub 5, our m will be equal to 1. And so when our m is equal to 1, our numerator will be 2 plus 5, which is 7. And that will be times 1 plus 2, which is 3. And that will be over 1 plus 1, which is 2, times 2 plus 3, which is 5. And like I said, this will be times our a sub 3, so this will be a 5 times 2 over 1 times 3. That'll be times our a sub 0. And once again, I'm going to calculate one more coefficient, but it appears that each successive numerator will cancel the denominator with the exception of the 3, which is in the denominator from our first term, which will linger. But just to make sure it'll linger, like I said, let's calculate our third coefficient here. So we have a sub 7. When we have a sub 7, that means our m is equal to 2. So when we plug in m equals 2 into our formula, we will have a 2 times 2, which is 4, plus 5, which is a 9 for our first term in our numerator. Then for our second term, we will have 2 times 2 plus 4, which is 8 in our numerator. And then in our denominator, we will have a 2 plus 1, which is 3 in our denominator. And then that will be times a 2 times 2, which is 4 plus 3, which is a 7. And that'll all be times a sub 5. So we have 7 times 3 over 2 times 5 times 5 times 2 times 1 times 3 times a sub 0. Great. So let's go ahead and squeeze in our definition for our a sub 2m plus 1 here before we erase and write out our final solution. And I went ahead and changed those a sub 0s to a sub 1s. I accidentally wrote a sub 0 when dealing with the odds. It looks like I missed this one as well. But yes, a sub 1 is the free variable corresponding to the odd coefficients, obviously. So we have that a sub 2m plus 1 is equal to the following. So if you'll notice, the only terms that persist through each new iteration of our coefficient is just the new numerator, which is represented by 2m plus 5 times m plus 2. And then we have that lingering 3 in the bottom, and this will be times a sub 1. So this is the general form of our odd coefficients for this series solution. Great. So let me go ahead and make some space by erasing this, and then we can go ahead and write out our solution. So now that I've made some space, let's go ahead and write out our solution to this differential equation. So our solution will be given by y is equal to, we'll go ahead and write out our a sub 0 for our even terms first, and we will have the sum as n goes from 0 to infinity of our calculated coefficients. We will have m plus 2 times 2m plus 3, and that will be times x to the 2m. That will be plus our odd coefficients, which will be given by a sub 1 over 3. We'll just go ahead and extract that constant 3 out, and we'll be left with the sum as n goes from 0 to infinity of our m plus 2 times our 2m plus 5 times x to the 2m plus 1. And this will be our final solution to this differential equation here. Great. So now let's go ahead and get into our third and final example. Okay, so for our third and final problem for this example video, we want to find the power series in x for the general solution of the differential equation 1 plus x squared times y double prime minus 10xy prime plus 28y is equal to 0. So to begin, just like the other two problems, let's go ahead and extract the coefficients for this differential equation. So our alpha is just going to be equal to 1 as we have no coefficient on our x squared term there. And then our beta will be equal to negative 10. And lastly, our gamma will be equal to our 28 there. Great, so let's go ahead and plug these in to calculate our p of n. So our p of n is going to be equal to n times n minus 1, as we don't have a coefficient on our alpha there. Then we'll use our beta here. We'll have a negative 10 times n, and then lastly a plus 28. So just like we have been doing, let's go ahead and multiply this out and see how it factors. So we will have an n squared minus n minus 11n, which will be minus 11n, and then lastly plus 28. So we can see that this will factor in the following way. We will have that this is equal to n minus 7 times n minus 4. Great. So let's go ahead and plug this value for our p of n into the definition of our a sub n plus 2. Well, that's going to be equal to a negative out front, and since this p of n does not lead with a negative, we will have to use that negative here. Then our p of n will be in the numerator, so we'll have an n minus 7 times n minus 4 over our numerator, which will stay constant, which is just n plus 1 times n plus 2. And that will be times our a sub n for n greater than or equal to 0. Great. And so from here, we want to split this up into our even and odd coefficients, just like we've been doing. So let's start with our evens here, because we have no cancellation, unfortunately, in our a sub n plus 2. So our evens will simply be a sub 2m plus 2, and that's going to equal a negative. We'll have p of 2m in the numerator, so that will give us a 2m minus 7 times a 2m minus 4, and that will be over 2m plus 1 times 2m plus 2. That will be times a sub 2m for m greater than or equal to 0. Now, just like we did in the last problem, we are going to extract a 2 out of our numerator and denominator, specifically these terms that I have marked with this arrow here. And so once we simplify that by factoring out the 2's and canceling them, we will get that this is equal to negative 2m minus 7 times, we'll be left with an m minus 2 in our numerator, and that will all be over a 2m plus 1. And once we cancel out that 2 in the denominator, we will have an m plus 1 there. And this will be times a sub 2m, once again for m greater than or equal to 0. So from here, let's go ahead and compute some coefficients to figure out what the general form for our coefficients in this problem is. So to start with, let's start with our a sub 2. When we have a sub 2, our m will be equal to 0. So we'll be left with a negative 7 in the numerator there, and a negative 2 also for our second term. And I don't want to forget our leading negative, so I'll just put it right there. Then for our denominator, we will have 2 times 0, which is just 0, and that will leave us with a 1 times 1 in our denominator here. Great. So next, let's calculate our a sub 4. When we have a sub 4, our m is equal to 1, so let's go ahead and plug that in here. So we'll have a 2 times 1 minus 7, which is just equal to a negative 5. And then we'll have for our second term a 1 minus 2, which is just equal to a negative 1 here. And once again, we'll have a leading negative there. And then in our denominator, we will have a 1 plus 2 times 1, which is 3. So we'll be left with a 3 times our m plus 1, which will be a 2. So we'll be left with 3 times 2, and that will be times our a sub 2, which is another negative out front, negative 7 times negative 2, all over 1 times our a sub 0, which I forgot to include here, so let me just try to squeeze it in right there. There we go. Great. And so from here, I want to go ahead and note the following. When we are considering our a sub 6, our m will be equal to 2. But if we have m equals 2, we will get a 0 in our numerator for this term here, which will carry over to all successive coefficients. So I want to note that a sub 2m will equal 0 for all m greater than or equal to 2. So our coefficients that we are left with, well, let's calculate our a sub 2 is going to be equal to a negative 14, and our a sub 4 is going to be equal to a 35 over 3. Great. So let's go ahead and do our odd coefficients next. So for our odd coefficients, we will have a sub 2m plus 3 is equal to, well, we'll have p of 2m plus 1. So let's go ahead and not forget our leading negative here before we calculate that. So if you remember, the factorization for our p of n was n minus 7 times n minus 4. So when we plug in our 2m plus 1, we will be left with a 2m minus 6 times a 2m minus 3 when we plug in our 2m plus 1 there. and our denominator will stay the same. We will have a 2m plus 2 times 2m plus 3, and that will be times a sub 2m plus 1. So let's go ahead and see if we can cancel things, and in fact we can by extracting out the 2's as we have done previously, and once we do that we will get our leading negative here, and that will be times m minus 3 times 2m minus 3 over m plus 1 times 2m plus 3, all times a sub 2m plus 1. So let's go ahead and calculate our coefficients. So our first one is going to be a sub 3. When we have a sub 3, we will get a 0 for our m. And so when we get a 0 for our m, we will get a negative 3 for the first term of our numerator, as well as a negative 3 for the second term of our numerator. And that will be over a 1 times a 3 for our denominator times a sub 1. Next, let's go ahead and calculate our a sub 5 here. Well, our a sub 5 is going to be when m is equal to 1, so that will give us a negative out front for our numerator. And then when we have m is equal to 1, we will have 1 minus 3, which is a negative 2. And then for our second term in our numerator, we will have a 2 minus 3, which is simply equal to a negative 1 there. And that will all be times a sub 3. And then in our denominator, we will have a 1 plus 1, which is 2, so we'll have a 2 there. And then we will have 2 times 1 plus 3, which is a 5 for our denominator there. And now let's go ahead and calculate our a sub 7, which will be when m is equal to 2. And just like before, when our m is equal to 3, we will not have any more coefficients, as we will get a 0 in our numerator. So this will be our last coefficient we need to calculate. So we will have a sub 7 is equal to the following. So when we have a sub 7, our m will be equal to 2. So when we have a 2 in our numerator, we will have a negative, and then for our first term, we will have 2 minus 3, which is a negative 1. Then for our second term, we will have a 4 minus 3, which is just a 1 there. And that will all be over our denominator, which is 2 plus 1, which is 3. And that'll be times a 2 times 2, which is 4, plus 3, which is a 7. That'll be times a sub 5. And that's all we need for our general solution, because our a sub 2m plus 1 is equal to 0 for all m greater than or equal to 3. Great. And so from here, I'll go ahead and write out the general solution for you. And so there we go. We have the following value for y, which is our general solution, given in terms of the coefficients we calculated. We have a sub 0 times 1, which is our first general term, minus 14x squared plus 35 over 3x to the fourth, plus a sub 1 times x minus 3x cubed plus 3 over 5x to the fifth, plus 1 over 35x to the seventh, which gives us our final solution to this differential equation. So that finishes our last problem off, and that's a good place to stop.